So for question 2, benzene vapor at 580 degrees Celsius and 2 atmospheric pressure is fed to a continuous condenser exiting as a liquid at 25 degrees Celsius at a flow rate sufficient to fill a 1.75 meter cube drum every 2 minutes. Please take note of this. And calculate the rate in kilowatts at which heat must be removed from the condenser. So you are given hints here that you are free to choose a reference state to make your calculation easier. We'll get to that later. And pressure has negligible influence on the enthalpy of ideal gases. So from table 1 we obtain the properties of benzene, the chemical properties of benzene. So the molar weight of benzene, the specific gravity of benzene, and the boiling temperature of benzene, which is 80.1 degrees Celsius. And we'll take this as our reference temperature. And the difference in the enthalpy of vapor phase of benzene, which is 30.765 kilojoule per mole. So since we are given the specific gravity of benzene, we can calculate for its density. So multiply the specific gravity of benzene with the density of water, we get 879 kilo per meter cube. So to obtain the molar flow rate, which is the N dot here of benzene, so because we were given that it is 1.75 meter cubes in 2 minutes, so we have to divide it by 2 minutes. This is a flow rate, okay, and multiply by its density, divide by its molar weight, and convert them into seconds. We get 0.1641 kilomole per second, or 164.1 mole per second. Okay, so we use the process pathway approach. So basically our benzene changes from this state to this state here. So in order to calculate the change in enthalpy from this state to this state, we'll take the process pathway approach. So we first calculate H1 and H2, which is the change from 580 degrees Celsius to 80.1 degrees Celsius, and we calculate from 25 degrees Celsius to 80.1 degrees Celsius. So for H1, we integrate 80.1 to 580 degrees Celsius and of the heat capacity. So this is a fixed formula. It depends on the table that you are given, in which in this case we can obtain the formula from table B.2. So depending on the units and stuff, you may have different A, B, C, and D, so please check carefully. Okay, you can get this formula from the above the table written there. So this is the formula, and we have to integrate this as a function of temperature. So after integration, you get AT plus B over 2T squared. I hope you remember your integration. And integrate it from 80.1 to 580 degrees Celsius. So substitute them in, substitute your values in, substitute your A, B, C, and D in, which you can obtain from table B.2. And that leaves you the change in enthalpy in the first pathway is negative 77.53 kilojoule per mole. So we do the same thing for H2. So we will integrate it from 25 degrees Celsius to 80.1 degrees Celsius, which is from here to here. So same thing, integrate this equation, which gives you this, okay, it will give you same thing as this. We'll substitute the A, B, C, and D values in, and substitute the temperature values in. Okay, 20 minus 80.1, 25 minus 80.1, their squares, and you get negative 7.699 kilojoules per mole. So actual change in enthalpy is H1 plus change in the vaporization, the delta H of the vapor state, plus H2, and this gives you negative 115.7 kilojoules per mole. So this one you can already you obtain from the table itself, right? Which was here. Okay, so we use that as a reference state. So to find the actual rate of the heat removed, we calculate for the Q. And in this case, so because this is a specific enthalpy, we need to multiply by its molar flow rate. So delta specific enthalpy multiplied by its molar flow rate that we have calculated earlier on gives you negative 19 times 10 to the power of 3 kilojoule per second, which also equals to this kilowatt.